Good morning, teachers. My name is PHUONG. I'm from Group 8, and this is my part to continue the last part of the Lab 3, an overview about cache memory and introducing the SMPCACHE. So, in these presentations, I mainly discuss the following sessions, including the replacement algorithm, graph policy, introduction to the multiprocessor system, cache coherent problem with its solutions, the burst arbitrations, introduce the SMPCACHE, and my results of the project 1. So first of all, we come to the first part of my presentations, the replacement algorithm is an important part of the memory management in a computer system. And we use it to optimize the memory usage. There are some common replacement algorithms we can see in our computer system. They are the LRU, LFU, FIFO, the clock, or other variant style like the enhanced second chance or the NRU and the random. Over here, I compare some replacement algorithm exactly for the LRU, LFU, FIFO, and the random. First of all, we come to the LRU, or stand for the least recently uses. It evaluates a page based on the time of access. The most recent user's page will be remembered, while the least user's page will be displayed, and probably is the most effective algorithm in the computer system. The LRU performs well when there is temporal locality. Well, the second algorithm I want to mention is the LFU, or we call the least frequently used. When a page is needed, the LFU algorithm uses the frequency table to track the number of visits per page over a period of time, and when the cache is full, the LFU evicts the item with the lowest frequency count from the system. So this type of algorithm is more suitable for the skill access patterns where a few items are repeatedly accessed. Additionally, I compare the FOFI, it stands for the first in first out algorithm, with the others. Well, to be honest, it is the simplest algorithm of all, because the FOFI works like it replaces the first page brought into the memory, which means the cache has been inserted for the longest will be replaced. And because it's simple, but it doesn't care about the usage level of the page and can cause the related anomaly. Well, this phenomenon known as the FOFI anomaly are in the cache replacement algorithm, where increasing cache size can lead to the increase in the cache misses. Last replacement algorithm I want to mention today is the random. Random algorithm chooses one of the random page instead and then evicts it from the system when the cache is full. Well, although this is not optimal, but it's simple and easy to implement. The second section I want to introduce about the graph policy. It refers to the strategy or the approach used to handle the graph operation to memory or storage. The graph policy optimizes the performance of the computer system by reducing the latencies, the bandwidth requirement, maintaining cache coherence, and ensuring consistency and reliability in the data modifications. Different graph policies exist, and they have various trade-offs between performance, cache coherence, and data consistencies. There are two common types, the graph tool and the graph. The graph tools mean all the graph operations update both the cache and the main memory simultaneously, when the graph is that the graph operations are usually made only to the cache, and the memory is only updated when the corresponding cache line is evicted from the cache. So the graph tool will ensure the consistent information between the cache and the main memory, but take up a lot of the system burst bandwidth and processing time, while the graph take up less system burst bandwidth and processing time. Also in these presentations, I want want to introduce the multiprocessor system, which is known as the parallel computer or a multiprocessing system. What is a computer system that consists the multiple processor and the central processing units, or we call CPUs, working together to execute the task. So the multiprocessor system provides the numerous benefits, including the increased performance, enhanced scalability, the increased throughput, and improved reliability and fault tolerance. However, this multiprocessor system also presents challenges such as the parallelization overhead, the scalability limitations, the complexity. But despite these challenges, the multiprocessor system remains a powerful platform for parallel computing and enable faster and more efficient task executions, making them widely used in various domains such as the scientific research, data analysis, simulations, virtualizations, and high-performance computing. There are two common types of the shared memory system. Is the SMP stand for the symmetric multiprocessor system, and the DSM stand for the distributed shared memory system. In both types of organizations, each processor can reach and write to any part of the system memory. However, the SMP system usually have an equal fast memory area for all the processors, also known as the Uniform Memory Access, the UMA. On the contrary, the DSM system had many memory areas, and the latency in the memory access operations will depend on the relative locations of the processor and the memory. They call the cache coherent non-uniform memory access. Otherwise, the SMP system had advantage over the shared bus architecture because these architectures only need to use one bus a byte. The cache association problem is simpler because the memory is accessed at the speed equal to the speed of the lowest processor. This limits the ability to further expand of the processor. In contrast, the DSM system are scalable because the local memory areas can be accessed very quickly, and the DSM system only work well when the operating system supports the NGUYEN access. There will be problem about the cache coherence in the computer system, and it's a change in the multiprocessor system where each processor has its own cache memory, and this problem refers to the potential inconsistencies when multiple caches store copies of the same memory locations, which can become out of sync or inconsistent. The cache invalidations and update involve coordination and the communication to maintain the consistency in the shared memory allocation. Maintain cache coherence require proper memory ordering and synchronizations across the multiple processors. Thus, ensuring the cache coherence minimizes additional overhead, impacting the system performance and making it a key challenge. There are some key concepts related to the cache coherence problem. Is the coherent protocols, which is the most cache coherence protocols are designed for caches with a private process, the shared memory access, read and write coherent traffic. I feel there are three solutions for this problem. It is the software solution, hardware solutions, and the memory barriers and synchronization. About three solutions have been mentioned before. We come to the first solution, the memory barriers and synchronizations. So the methods is, in addition to the cache coherent protocol, the synchronizations mechanisms like memory barrier, lock, and atomic operations can be used to enforce the ordering and consistency in accessing shared data. The second solution is a software solution, but the software cache coherent screen uses a compiler and operating system to avoid additional hardware, circuitry, and logic, transferring the design complexity from hardware to software. This mechanisms analyzing the code to identify and save data items for caching, preventing a non-cacheable item from being cached. The last solution is the hardware solution, and the hardware-based cache coherent protocols will improve the performance and reduce the software development burden by the dynamic code recognizing potential inconsistencies at the runtime, categorized into the directory and the sloppy protocols. About the directory protocols, the directory protocols involve a centralized controller and directory in the main memory. To maintain the global state information about the local cache, so the controller checks the data transfer between the memory and caches and keeps the state information updated. The processor requests the exclusive access to lines, invalidate the copies, and issue command for read-only access. So this protocol effective in the large-scale system with complex interconnection scheme. The second protocol I mentioned here is the stopping protocol. While the stopping protocols distribute caches among the controllers in a multiprocessor, allowing each to snoop on the network, and they are the best suited for the burst-based multiprocessor, but the local caches can be used to avoid the burst accesses. There are two basic approaches to the snooping protocols. We call it the invalidate and the write update. About the write invalidate, this approach is widely used in commercial multiprocessor systems, marking the stage of every cache line as modified and exclusive E, shared S, or invalid E. With the DSM system, there are the protocols MSI and NESI, but with the SMP system, we use both the MSI, NESI, and the Dragon. About the burst arbitrations, I have mentioned before, there is a process in the computer system to determine which device or processors have control over a shared bus. It ensures the fair and efficient coordinations of the bus access among the competing devices and preventing the conflicts. There are various bus arbitration methods. Here I have the centralized arbitrations, distributed arbitrations, data training, priority-based arbitrations, and the last one is request, or we call the grant protocols. In the centralized arbitrations, these methods involve a dedicated hardware component managing the bus access, granting access beyond the predefined prioritized scheme to different devices or processor. The distributed arbitrations involve the competing for bus access using algorithms like round robin, random, or token-based scheme, with device monitoring the bus status and requesting a sequence available. The data training method is a system where devices or processors are interconnected in a chain-like structure, with each device passing control to the next, continuing a continuous loop. And the priority-based arbitrations will assign the devices or the processor different priority level based on the importance, urgency, determined assessment, giving a higher priority limits the priority access to the bus. And the last one is a request or grant protocols, is a protocol where the device or processor requests access to a bus with the permission granted by the bus operator based on a predefined algorithm or the priority scheme. So you can see that there are a lot of methods of the bus attributions. So the choice of the bus attribution methods will depend on the factors such as the system architecture, the number and type of device, performance requirement, and the design fairness and efficiency of the bus access. So different systems may employ different applications techniques to suit. And now I'm introducing the simulator SMPCACHE. So first we come to how to use these simulators. Firstly, we need to get these simulators in our computers. We can download the appropriate versions from the link here. So this is the interface of the SMPCACHE simulator for cache memory system on multiprocessor. After understanding the instruction, features, and the functions of the simulator, we will prepare the trace data. And here, the project one have prepared the data for us. So we just need to bring all this data into the simulators, and I will show you how. Firstly, in this configure, we click on the multiprocessor, main memory, and cache. So here we have the dialog box. Determine is the processor in SMP, one processor. The cache coherent protocol is MESE. And the scheme for bus attribution is random. The word wide is 60 bit, and the word by block is 62. Block in memory, in main memory. The mapping is for associative. Replacement policy is LRU. Okay, so after fulfilling the dealer's number, we will save the in case we have already had the configurations, we can load the configurations in this and then choose the folder over here. Okay, and then click OK. And then the configurations we have saved will be saved in our system. Number one, this means the main memory size, how many bytes. So here in this case, we have the block size is 32 bytes. The block in main memory is 8,192. So the main memory size will be the size of a block multiplied by the number of blocks in the main memory, which is 32 multiplied by the 8,192, which is 62,144 bytes. So this is the size of the main memories. The second requirement, it requires us to observe the miss rate in the cache access rate with the memory trace. I come to a statistical table. To answer the A section up to, do the program have the same level of locality? Which program has the best locality and which program has the worst locality? The answer is the lowest miss rate belong to the Hydro and the NASA 7 with 10.2%. This shows that the Hydro and NASA 7 have the best local coverage among this program, and the highest miss rate belong to the SWM with 32%. This shows that the SWN has the worst locality among these programs. And the second question is, do the above configurations exploit the localities of this program and increase the system performance, and why? Well, the answer is some programs such as the Hadron 97 and the LGD has the low miss rate below the 22% are showing the good localities, so the system configurations has well exploited the localities of this program, reducing the number of unsuccessful access and increasing the system performance. However, some other programs such as the SWM and the UCOMP have the high miss rate over 16%, indicating a poor locality. So this may be because this program do not make good use of the cache localities or have a memory access model that is incompatible with the current cache structure. During the program execution, if observed in graph form, the miss rate gradually decrease, and why? So it's true that the miss rate gradually decrease, and the main reason leading to the gradual decrease in the miss rate during the program executions is the locality of the cache and the cache replacement efficiency. So due to the cache locality and the cache replacement efficiency, the miss rate gradually decreases over time, and the foreign access tends to access already cached data block, thereby increasing the cache hit rate and reducing the cache miss rate.